Here we have an object which is released from rest at the point x and it is sliding to y. The vertical distance between x and y is given as 10 meters. During the motion, 20% of the object's initial gravitational potential energy is lost as friction. We need to find the speed of the object at y. Now, it is clearly mentioned that friction is acting on this object and friction is a non-conservative force. And we have learned that whenever non-conservative forces are present in the system, then mechanical energy conservation is a little tricky to apply. In this question, we can apply the mechanical energy question, but with a slight difference. If we recall the basic formula for mechanical energy conservation, we will write total energy at the point x will be equal to the total energy at the point y. Now, this law can be applied easily if there is no friction, but here the question has clearly mentioned that friction is acting. So, to work around this problem, let's focus on this statement. They have said 20% of the object's initial gravitational potential energy is lost as friction. So, let us write down the GPE at the point x. Remember the formula mgh? Now, 20% of this energy will be lost as friction. So let us write down the energy which is lost because of this friction will be 20%, which is 0.2 into mgh. So how much energy will be left? So let's write down the energy which is left. We will subtract it. So the total energy was mgh, out of which 20% was lost as friction. So if we solve this, we will get 0.8 mgh. And now the trick to solving this question is we have to account for friction. So how do we do that? So let's consider the original image. So the object is sliding from x to y in the presence of friction. So let's consider this case. It is having friction. Now consider another situation where the diagram is the same. The object is going from x to y, but here we say there is friction does not exist. So let's say without friction. So in case 1, energy at x was mgh and we saw that 20% of it is lost as friction. Now in case 2, which does not incorporate friction into the picture, we can consider that the total energy of the object at the topmost point will be this only 0.8 mgh. So in the case when we are considering friction is not there, in that case we will write the energy of the object at the topmost point will be equal to 0.8 mgh. And now we can very easily apply the law of mechanical energy conservation, which states that the total energy at x will be equal to the total energy at y. Now total energy of the object at x was 0.8 mgh. This will be equal to the kinetic energy at y plus potential energy at y. Now, since y is on the ground, potential energy at y will be considered as 0 and kinetic energy at the point y, we will write half mv square. So let's write 0.8 mgh is equal to half mv square. And let's try to simplify this. If we cancel out m from both sides, and let us try to make v as the subject. So we'll get v is equal to square root of 2 into 0.8 into g times h. Now, if we look at the options, the answer for speed of the object at y, all the options, the speed is given in terms of g. So we will not put the value of g. Instead, let's put h as 10. So we will write square root of 2 multiplied by 0.8 multiplied by g multiplied by 10. And let's simplify this further. So 2 into 0.8 into 10 will come out as 16. So we'll have a 16g under the root, and this can be simplified to 4 root g. And that is the speed of the object at the point y. And let's go back to the options. 4 root g exists in option C, which is the correct answer. An object is released from rest and it slides down a frictionless ramp. So initial speed is 0 and the ramp does not have any friction. The object then leaves the ramp and slides down a rough horizontal surface. The object stops in a distance s along the ramp. So the final velocity is equal to 0. The coefficient of dynamic friction is given as mu. We need to find the height of the ramp. Now in this question, the frictional forces are involved. Friction is a non-conservative force, so it is easier for us if we can apply the work energy principle. So let's write down the formula. Total work done by all the forces acting on the object will be equal to the change in the kinetic energy, which can be written as kinetic energy final minus initial. Now, final kinetic energy is 0 as well as the initial kinetic energy is 0. So the change we can write is 0. which means whatever is the total work done, that will add up to zero. And let's see how many forces are acting on this object. So while the object is moving along the ramp, you will have the gravitational force mg acting downwards, and then we have the normal reaction. Now, when the object is sliding along the rough surface, it is having mg, the gravitational force, with the normal reaction. Now, since the surface is having friction we will draw towards the left hand side. So we have three forces while the object is moving on the rough surface. So let's proceed. Work done total will be equal to work done by the gravitational force plus work done by the normal reaction plus work done by friction. All of that will add up to zero. Now, work done by all conservative forces is given by the formula negative of change in potential energy. So work done of gravitational force will be equal to negative of change in the gravitational potential energy, which can be simplified to GPE initial minus GPE final. So initially the object is at this point. So the gravitational potential energy will be mgh. So let's write down initial will be mgh. And finally, the GPE will be zero because by that time the object would have come over here. This point is on the ground, so potential energy will be zero. So the total work done by the gravitational force is mgh. Now for the normal reaction, work done by normal reaction is always zero because the angle between the normal reaction and the displacement is always 90. So in this case, let's say if I draw a tangent here, this will be the displacement. So the angle between normal reaction and displacement is always 90 degrees. And that is why we say work done by normal reaction is always zero. And finally, coming to the work done by friction. So we will use the basic formula for work, which is Fs cos theta. Now force is friction, which will be written as mu times the normal reaction multiplied by displacement into cos of theta. Now, if we go back to the diagram, when the object was sliding on the rough surface, normal reaction will be equal to mg. So let's write down friction will be equal to mu times mg multiplied by s is the displacement. Now theta is the angle between the friction and the displacement. So in this case, the object is sliding forward, so the displacement is towards the right. Let me repeat, since the object is sliding forward, so the direction of displacement is to the right, but friction is to the left hand side. So the angle between friction and S is 180 degrees as they are opposite. So we will write 180 here, cos 180. And now if we simplify this expression, we will get negative mu mgs as the work done by friction because cos 180 is minus 1. Now let us put all the expressions in the work energy principle. So work done by gravitational forces mgh. In fact, let me write down the entire expression one more time. Work done by gravitational force plus work done by normal reaction plus work done by friction is equal to change in kinetic energy. The delta K we had deduced earlier to be zero. Work done by gravitational force is mgh. Let's write it down. Work done by the normal reaction is zero, and the work done by the friction will be negative mu mgs. Now let's go back to the question to identify which parameter are we supposed to find. We need to find height of the ramp, which is h. So let us try to make h as the subject. So in this expression, if I take minus mu gs on the right hand side, we will get mgh will be equal to mu mgs. M will get cancelled out from both sides, and also G will get cancelled out from both sides. And if we make H as the subject, we will get mu S as the answer. And let's go back to the options. Where does mu into S exists? It is option D, and that is the answer for this question.